Hello everyone, welcome back. This is 3-2 Planning in the Compact Redstone series. I'm Immune222. So this is basically a continuation on 2-12 Introduction to Planning and Sequencing, where I've already talked about some methods for planning and sequencing, and as shown in this video's title, we are going to deepen our understanding in planning. So in 2012, Introduction to Planning and Sequencing, we briefly discuss the planning steps at the preparation stage. Now, of course, after the preparation stage, we will have the building stage. So now we are going to deepen our discussion in these planning steps and discuss the planning steps at the building stage. So before I start this video, just to tell you that, of course, the content in this video might be helpful for some of you, but then the most important thing in Redstone is still doing it by yourself. So while you may gain some valuable information from this video, you also have to bear in mind that you also need to apply what you have learned in building actual doors instead of just hearing it and not doing it. So yeah, and of course, because we are in the third series already, so this is the advanced series, I would have expected you to have all the knowledge from the first and the second series. So the intermediate series basically is the second series. So yeah, I would expect you to have some well-versed Redstone knowledge already. So I would have expected you to build a 5x5 or even a 6x6 door, and you might have also attempted some 5x5 pattern doors, 6x6 pattern doors as well. It might not be an optimal size or optimal speed, of course, but hey, that's why you're here. So so the first topic I want to talk about is how you would apply the circuit flow principle and the input position selection principle as taught in 2-12. So I just refer to these two doors, which I've already briefly discussed on in 1-5 input methods. So if you want to check that out, then there will also be a links in the Word file. That will be in the drive folder, as well as the Word download as well, of course. So yeah, that's always what I've done. But yeah, either way. So yes, so let's just see here. So we will have a piston layout here. And also, I guess also the entire circuit as well. For the 297 block 5x5 vertical bar door by me. So here we are interested in, knowing how to design some circuit flow or how to select input position. So let's go to here, this side here. We would notice some characteristics of the slime extender. So we have to think about how to make this piston layout work. Now, the first thing is that we will have some covering pistons here and here. So they will need to be retracted like this before we push the slime extender. So yeah, these two pistons basically. Because otherwise, this observer will push this block in front and you can never retract it. This is also kind of similar, but then this is a bit different because if we don't retract it, then when this this slime extender retracts, then we'll have here. Obviously, you can also have some alternative solution. For example, placing a piston here to push it back, but then in here we use this layout instead. So yeah, but the idea is very similar. So you have to retract your your covering pistons before you push and pull the slime extender. And obviously, after the slime extender is retracted, you would need to push them back. So yeah, so that's the first thing you have to remember. So these are some timing dependencies basically. The second thing is that the slime extender actually requires several initiating moves before extending. So why do I say that? If you try to push one, it doesn't work. The reason is very simple. It exceeds the push limit. So what you need to do is to, for example, do some of this. And then this is still not enough. So in the actual door, which you see here, what it will do is actually it will check. So yeah, you see this actually constantly extends. So which will make these pistons not stick to the slime extender. And then now you can freely push your slime extender. Or I should push the bottom one. Like so. So yeah. So the summary is basically that, we would need to push these pistons here. And then we also have a circuit which will push these pistons such that they do not stick to the slime. And yeah, before we can even power a circuit on the top which will actually control the entire slime extender already. Now, when you're trying to wire the door, you will have some insights. So here, one of the insights is that the bottom only has space for completing the initiating moves, which is, to power the pistons here and to constant power the pistons here. So the bottom only has this kind of space and no other space for doing other stuff. Those have to be controlled by the top. Now, what does that mean? Remember that the initiating moves has to be powered first before you can power the slime extender. So the circuit flow principle, what it would suggest is to have the bottom first to the top. Okay. So that's the first thing. So this is basically a time dependency problem. Now, in addition, we also have established previously that we will have these covering pistons which need to be retracted before the slime extender and push after the slime extender. Or let me specify more correctly. Pull before the slime extender extends and push after the slime extender retracts. So you see this is an arbor circuit. Now, an efficient solution would be to design hopper ROMs to control these two pistons and as well as this one. And also in related that this needs multiple pulses. And a hopper ROM does that very nicely. Now, because we already said that we need to do some initiating moves, it is very obvious that if we fit our initiating move circuit on the left side, we won't really have any more space for the hopper ROM. So it must be positioned on the right. And what would the input position selection principle say? We would basically have a lever input on here. For example, this here. Then, we have a good advantage because we have already controlled these two pistons. And we can also directly connect to a hopper timer, something like this. And by doing so, because we already have these two pistons connected, and also the hopper timer basically also connected very directly, we will help leave out the right to control what we have here, which is the singles and the double extenders. And also some other circuits which will transmit some signals to the left, which you see we do it by here basically. So this kind of thing here, and then yeah, basically like that. So by strategically choosing an input, something like this, we have essentially reduced our wiring difficulty and increase our wiring efficiency. So hopefully this example, gives you a brief understanding on why we would select an input here based on some facts on the slime extender. The slime extender is probably the harder circuit to control in this door. So yeah. Now, notice that for this layout, we choose a lever input and a input position at the bottom here. But then for the exact same door, just with a different layout, it completely changes our mindset. So which basically I'll demonstrate now is that we would choose, an input here with a button input instead. And I'll of course talk about why. So let me just reset this first. Okay. So now we will go on to this one, which is slightly larger because it doesn't use line blocks. So this is by me and Image009. You will see in the later door that I also collaborated one of the doors with him as well. So now this time, the hardest part is on the right side, which is the triple extender. I'm sure you can see why already. Now, we do some efficient wiring methods by connecting the double extender and the triple extender together using either a long pulse for the triples, because you can imagine that the triple can do a very long pulse, and then we will have the fronts that will do its stuff, which will basically extend these kind of stuff. And then once it's over, then we can retract the back pistons, and then the other circuit will do its stuff as well. So this is a very common method for controlling our triple piston extender. Then, of course, we can do a long pulse or just two distant one-tick pulses as well. It doesn't really matter. It just depends on which one we prefer. So again, if we follow the input position selection principle, then we can have a button input that's literally just here. We don't even need to create a circuit for the two distant one-tick pulses, because a button literally behaves as a long pulse already. So it's very nice. And then we just place it like here, such that it will, of course, going to power the back pistons of the doubles and the triples. Then this, of course, will also reduce wiring difficulty and increase wiring efficiency. Yeah, because as I've said, we don't even need to create the two distant one-tick pulses. We can just directly connect it like this. So we have reduced the need of space. Now, by doing so, we have already established our circuit flow. So you can see it's a bit different than this scenario, because in this scenario, we have, analyzed a lot here. We have also do some planning here to see that, we need a hopper ROM, but then it doesn't fit, so we have to place it here. And this also determines our input position, but here is different. Here is we have decided an input position first, and then we would decide the circuit flow. So you can see this kind of interchanges. It really depends on how your piston layout behaves, and then to see which one works better for you. So yeah, so you have to have a flexible mindset in here. Then the circuit flow would be basically from right to the left, because we have already decided, the input to be here. Then of course it's from the right to the left. Where else could it be? So yeah. So hopefully these two, examples give you a better idea on how to select your input positions and to decide on your circuit flow. But then there are always some other situations that, yes, we know an exact circuit flow, but we cannot decide an input position yet. Because perhaps the door, there are a lot of positions where it seems that an input is viable there, but you just have to try some things out. So basically, it's not obvious where input position would be suitable. For example, funnel doors, which is basically the next example. So what do you do then? Now here comes our first concept in this video, is that when we have established a circuit flow, but we cannot decide where exactly to place the input, then we simply just keep building some useful circuits, some small circuits that will control our extenders. And then it will later, there will be some apparent constrictions such that you would know where exactly to place your input. Or, some circuits that will heavily rely on an exact input. So, yeah. So the example is here. The 780 block 7x7 funnel by me and Imager again. So now, based on this piston layout, I'm not sure if you have noticed it, but this is a very standard bottom single double layout, and the rationale behind it is fairly straightforward. So we have this here, then connect to here, and then when we need to do the singles, we'll do something like this. And I guess I also have to do a return here, but we'll do that later. So you see this two will extend, and then in here, let me see. In here, let's do something like this. So it will always be 2 ticks apart, because 2 ticks apart allow the retraction, as you will see here. And then when we need to do the singles, we will do this, and then this. And then now for the opening, because we need the singles, these door blocks, to act as solid blocks for the double extender. So we will do the singles first, then we will do a double. So yeah, so hopefully this makes sense for you, in case you wonder how the piston layout works. Okay, so you see already from here that we need an arbor circuit. Very obvious. In the closing, we need the double and then the single. In the opening, we need the single and then the double. Arbor circuit. And of course, because this piston layout has all the sliders pushing initially from the left first, so we already have a solid idea of placing the input at the bottom left of the door. But then for this kind of door, it's not very obvious that where you should put it, right? Here it might be suitable, or here might be suitable. You're just not sure, right? Now, as I've already said, an arbor circuit is needed, so a hopper timer is needed, basically, because that's one of the most efficient methods of wiring an arbor circuit. So we just continue building some useful circuits. So, for example, we might also consider the triple on how it's going to fire. And then later, we will have noticed that we will build something like this. Basically also in consideration of triple, which I haven't included here. And yeah, eventually, we would know that a hopper timer, we can only fit it in here. And that's why an input is done here. So yeah. And yeah, and because the hopper timer is here, so input here, and yeah, we're done. So hopefully, this example demonstrates to you, you don't have to worry too much on selecting an input position very early during the building process, because a lot of the times you don't know. Of course, there's some doors that you would know immediately where to place your input, because there's very few positions which can reduce your wiring difficulty and increase your wiring efficiency. For example, like the cave door here. So you would know very immediately that you need to place it either at the bottom or at the top. It really just depends on which way you like to wire your circuit flow. But otherwise, when you don't know it, then you just keep building some useful circuits for the triple, for the double, etc., etc. And then eventually you'll find a position where you need to fit your hopper timer. In this case, then you know where your input is going to be. So yeah. Now, we have talked a lot about, how to select inputs and then some circuit flow principle, but then I haven't really talked about some common circuit flow directions. So now this is what we are going to discuss. Now for non-standard doors, what do we mean by non-standard doors? It just basically means the door is not flat. So not a 4x4 door, not a 5x5, 6x6. We'll have 4x4 cave, 5x5 funnel, 6x6 double cave corners, something like that. So these are non-standard doors, pattern doors basically. There are several types of common circuit flows that you can use to wire a door. And when I say circuit flows, I mean a very general context. So I don't really specify any specific parts of the top, bottom, left or right or front or back. So I won't say bottom left, bottom right, etc. Of course, you can go a bit more specific, but here I'm not going to go that deep into it. Because, we'll be here for quite a bit longer of time. So I just always refer it to top, side, or bottom. So now, if you are unsure about some circuit flows, some suitable circuit flows to use in your door, then you can always just refer to some existing piston doors and to gain a solid idea on what circuit flow is suitable. So now I'm going to introduce some few of them to, give you a good understanding of it. So first one would be spread base, which is shown in this diagram here. I will always use cyan glass as the first stuff to power, and then the blue glass as the last ones. And then in further more complicated examples, light blue will be the second one, and then we'll have the white glass as the third one. Blue will always be last, and cyan will always be the first. Okay. So spread flow. Let's say we have an input here. Then our circuit will of course go in a spread direction. What do we mean by spread? Well, it will just go to the nearest parts first. So example here, here, and here. Then it will go farther and farther, and then it will go here, and then here, and then until some very far, for example here. And until all areas are covered, basically. So we'll go to its neighbors first, then into the further neighbors, and then going to very far away. And you might already tell that this is very intuitive. Most doors are like that. Yeah. And this is the most common when we have some timing dependencies. For example, sliders, which we see here. Left must be applied first before the right. This is a timing dependency. Okay. Or the door requires a specific input position. For example, I think I don't really have a specific. Oh, here, for example, this one. Or the door is highly asymmetrical, which this door also is. It's not that symmetrical. You have a slime extender here, and then some double singles here. So that's the first circuit flow. The second one would be a top to bottom, or bottom to top, or front to back, whatever. Doesn't really matter. So the idea is very simple. It's already said in the name. So let's say we are considering the top to bottom, then obviously the input would be at the top. And then we first wire things at the top, then we wire things at the side, then we wire things at the bottom. Very simple indeed. Now, this would be most common when the layout is side symmetrical. So basically both sides are doing exactly the same thing, just mirrored. And the most complex part is either at the top or at the bottom. Usually, the input will be positioned where the stuff is more complicated, usually. But then this is not always the case. See 7x7 cave door there as an example. But usually size won't be the most complicated part. It'll usually be just top or bottom for top to bottom, bottom to top, usually. And a very similar neighbor of this is of course side to side. It is exactly the same, just rotated. So goes from one side to the other side. So this is the most common when the layout is side asymmetrical. Because if the sides were symmetrical, you probably won't want an input here and then just connect it to the other one. Because otherwise, if your sizes are symmetrical, then you basically need to do two side circuits, which is not that good. And the most complex part is either at the input position side or the opposite. So top and bottom won't be the most complex part. And last but not least, we'll have this here. I flipped it around for one reason I'll explain later. It's spiral. So as the name suggests, we'll go from here first, and then we'll wire it in a rotation manner. So we will wire this thing here first, and then this here first, this last. So when is this the most common? Only one. Sky doors, trapdoors. Yeah. For typical doors, this isn't really that common. Of course, there are some, but then it's not that common. So yeah. Now, one reason why spiral circuit flow really only appears in trapdoor or sky doors is because all of the four sides have similar powering properties. So you can imagine that a spiral door would, use a bit better in terms of wiring space. So because when you have, a spread flow, then you would probably have this space waste from here to here. You will probably have this space waste. But then spiral, you only would have, for example, this space waste. So, you can use a bit better in terms of circuit space. Yeah, you can maximize your circuit space usage, basically. And, it also minimizes the need of signal transmission, basically, because all of its neighbors are very close to each other. Unlike here, you might need some transmission here, which is basically a waste of space, you can say. Yeah, it's a bit more abstracted. Apologize. And of course, the circuit flow stuff involves some subjective judgment. So when I say, which is the more common, which is the less common, it really depends on what you observe, basically. And honestly, some circuit flows, like the world always has exceptions, So I just tell you what I observe, and you might agree, you might disagree. It's totally fine. But just suggesting to you that, these are YC, and then, I would suggest to you that when your door has these kind of certain characteristics, then I suggest you to follow a certain circuit flow. But then, every door has its own uniqueness, and there are always some exceptions. And therefore, you don't have to go very strict into here. And in fact, you don't really need to memorize these kind of circuit flows. You just have to, go under your mind that which kind of circuit flow are acceptable, you can say. Of course, there will be some circuit flows that are not acceptable, basically, which we will see in the exercises. There will be some circuit flows that you can see at the first glance that is not acceptable. It is very obvious. But otherwise, if there are no very strong reasons to against it, then those are acceptable circuit flow. So yeah. But anyway, let's just focus on some examples first. So I have 4 doors here showcased. So we will have the 297 block vertical bar. This has a spread based. Why? You can see from here, it will spread to here. It also spreads to here, and then it goes around like this, basically. So this is the farthest. These are the closer ones. This, and then go here. So yeah, it's a bit more weird here, but then this is indeed spread based. You can also argue it's top to bottom. Oh, sorry, it's bottom to top. It doesn't really matter. Yeah, one thing about this kind of circuit flow definition is that I don't go very rigorously. So you can always argue spread base is just any other circuit flow, essentially. It doesn't really matter. So yeah, spread base can be classified sometimes top to bottom, bottom to top, side to side as well. But yeah, not going to go that rigorous in the definition. You just gain a general idea on what I mean. Okay. So this is the 297 block one. You can argue it's spread based. You can argue it's bottom to top. It doesn't really matter. 1014 block. Okay, so this is the 7x7 cave. So the 7x7 cave is actually very obvious. It's bottom to top. So the size is symmetrical, and then the input is at the bottom, so it goes bottom to top, basically. And then we will have the 5x5 vertical bar door, but this time it's the 324 block one. this is side to side. I think it's very obvious. So it goes from one side and then it will go to the bottom and the top respectively, and then it will go to the other side as well. And then finally, I have this. I can show you the animation as well. So it's a bit more weird, but then when you analyze the circuit a bit longer, ignore this side and this side for now, then you see that the input is here. We don't connect to here. Instead, we go a full circle around. So it will connect to here first. And then here, it will actually go back to connect to here. It's a bit more weird. But anyway, it will go to here first, and then it will go in a circle. And then, it will go in a circle. So through here, and then go to here. So if we just consider these two sides, then you see very immediately that it is a spiral circuit flow. This might not be the best example, but then there are some other better examples that I've built that is very obviously spirals, a spiral circuit flow. So yeah. So at the end, why do I need to talk about circuit flows, the common circuit flows? That's because besides, following the circuit flow principle, which I've taught in 2-12, you can always check your piston layout and compare to other similar piston doors with similar characteristics, and, see what these similar piston doors have in common in terms of the circuit flow, and determine if your desired circuit flow for your piston door is appropriate. So yeah, hopefully you now have a better understanding on circuit flows, and you can always formulate your opinions on it and to decide which is better, because everyone has different wiring style, and you decide which one works best for you. So yeah. Now, after discussing, the circuit flow, the more applicational examples for the circuit flow principle and the input position selection principle, then now we actually go into talking about some planning at the building stage. So there are 4 aspects we're going to concern on. So the first one is signal transmission. So what do I mean by signal transmission? Which is basically what kind of circuits are best suited for our needs given our planned circuit flow and sequences, and of course the input position as well. The second one would be some strategies of connecting different circuits, because we want to match the needs of different circuits and sequences. So later I will talk about some connecting concepts. The third one would be some restriction of wiring space for future usage. So you might have heard of, volume restriction. You have restricted yourself in a certain volume in order to achieve a small door, but then there are also restrictions within the door itself. You might want a certain circuit component to be restricted within a certain volume, a certain space as well. So that's what I'm going to talk about as well. And finally, this is a bit more psychological than others, is the order on working on different circuit sections. Of course, I'll also analyze it, in terms of planning, but then it also involves a bit more psychological effects as well. So yeah, so the first part we're going to talk about is signal transmission. Now, in 1-10, signal transmission methods and basic miscellaneous circuits, we have learned various signal transmission methods already from there. And in 2010, entity usage and basic entity circuits, we also learned the wireless transmission methods. So I'm going to summarize, these together basically. And in compactors, we will have some transmission methods that, the common ones, which would be observer lines. While observer lines can be generalized as one-way transmission, basically. We also have sliders, and we also have the wireless transmission method. And we will discuss the properties of each transmission method and some appropriate situations for these methods. So first off is the one-way transmission method, which is the most common in all of the piston doors. You just basically connect from one side to the other without interference. So it has these certain properties. So they basically just transmit signal in one direction only. And besides Redstone dust, all other methods basically will induce delay from the input to the output. And they are very highly customizable in shapes and delay. So for example, an observer line, you may have a very straight line, or you can have a very snaky position. So, this is what I mean by flexibility in shape. And the layout, of course, because, for example here, maybe I want to make it into a hopper. Then we reduce one tick in delay. Or maybe I want to make it into a piston. Then I reduce another tick of delay. So you see a lot of different variations in shapes and delay. And this flexibility allows us to power components very easily along the way, because components might not be very well structured. It can go in a lot of different shapes, and one-way transmission methods allows us to do so. And circuits under this method can take multiple inputs and outputs. What do I mean by that? So let's say I have an observer line. Maybe I want to also power the output from another position. So maybe I will do something like this and then have a hopper here. Okay, perhaps maybe I want to output this in 2 positions. Then I go something like this. So you see multiple inputs and multiple outputs. So it's very flexible, basically. Now, after discussing, these kind of properties for one-way transmission methods, then let's summarize what appropriate situations we can use in here. So there are 3 points that I want to share with you. The first one is that if the circuit requires multiple signals or multiple input locations. Multiple signals, maybe it needs 3 pulses, or multiple input locations, as I've already said, because its flexibility in construction also means you can take multiple inputs. So this is a suitable situation. The second one is the outputs are highly non-linear. Because of the flexibility in the shape, we can always power stuff in a non-linear fashion. So say, for example, maybe let's do something like this. So very non-linear shape indeed. Then I have an input from here. Then I already powered this piston. Maybe I can power this piston like this, power this piston like this, go here. So that's one way, and that's what one-way transmission circuits can do. The other transmission methods, they can't do this. And lastly, the sequence of input and output components are similar. So you might wire a certain component first and do a signal transmission to another component. And if you can make sure that these components behave very similarly, then you can just wire a one-way transmission method, or I should say a one-way transmission circuit from your input to the output. And because they behave similarly, then you can make sure that these components will behave with no problems. So that's the appropriate situations in which one-way transmission methods would be useful. Now we will talk about another one, which is sliders. Sliders, unlike one-way transmission methods, they help to transmit signals in two directions. It should be pretty obvious to a lot of you that, for example, if you have a slider like this, you can go to this here and power this piston. You can go from here back to power this piston. So this piston powering this is one direction. This piston powering this is the other direction. So two directions. Their operation principle is very similar to SR latches. If you recall SR latches, when I power this piston, it would basically do something like a set. If I power this piston, it would do something like a reset. So you cannot set multiple times, it will just be in the set position, basically. If I do reset a lot of times, it will just be in reset position. Always. So yeah, so the operation principle is very similar to SR latches. Just imagine one of the piston is set, one of the piston is reset input. Then you can already see. They usually only have one input piston, but they can have multiple outputs. Multiple outputs is very simple. You can already see from previous example. I can have this, for example. So output here, output here, output here. Very simple indeed. Multiple outputs, but then usually one input piston. Of course, there will always be two pistons, but then I'm talking about one side. So one input piston. They are very limited in terms of the outputs because they have to align linearly. You can see it's very linear in terms of these outputs. And also, from an actual application, you can see that this observer can only power this and this. So yeah. So it's very linear in terms of the outputs. Now, I said before that they usually only have one input piston, but can they have multiple input pistons? Yes, but there's one catch. It's that the slider must be reset to receive another input because of the SR latch property. So for example, you might have something like this. You might have this power first, and let's say you block it. Actually, it doesn't need to. Like, let's say you want to power this piston, but then it's not in this position. You have to reset it before doing it another time. Let's say you power this piston first. You can power this piston, but it does nothing. Right? You have to reset it before you can, power this piston, for example. And of course, if you have one side here, you cannot just leave this, and then run the door another time because it won't do anything anymore. Then you always need to reset it, of course. So they require a control circuit for resetting. So after discussing all of these properties for sliders, then when is it suitable? The first is very obvious. The outputs are highly linear. So linear outputs, unlike the one I showed before in the one-way transmission methods. It is very non-linear, but then one-way transmission methods can deal with them very easily. The second situation is that there is a need for a long pulse or two distant short pulses. What do I mean by that? Now, consider this piston. I can have a slider that will do this, and then this here I can just connect to a delay circuit, and then later it will push it back to power this. And sliders helps with dealing with these kind of distant pulses. For a long pulse, you can very easily imagine just replace it with a redstone block, and then apply the same thing. And then after the delay circuit, do this. See? And the third thing is that multiple outputs are required to power near simultaneously. So for example, I have these two pistons. If I want to power them simultaneously, and of course the outputs are also linear, then I just do this. Then they can power at the same time. You might think, well, here is not really that much, but then when you have a lot of pistons, a lot of them, then you don't expect a one-way transmission circuit to do that. It might be space costly. Yes, you can obviously try to use redstone line to power it like this, but then sliders are usually more space efficient. So yeah, so these will be some suitable situations where sliders would be helpful. And then next I'll talk about one-way not one-way, wireless transmission methods. I'm not going to build anything here, unfortunately. So wireless transmission methods, as the name suggests, they would have these certain properties. Wireless transmission methods, they are very similar to one-way transmission methods, but what is different is, I'll list them a bit more further down. But yeah, as I've said, it's very similar to one-way transmission method in the sense that because they also transmit signal in one direction only. So from what you hear, you will think that it sounds very similar to one-way transmission methods, but then they are actually very different. Now let's talk about the difference. So circuits under this method have two separate circuits, and they don't have any circuit connection in between them. So let's just build something, yes, small. Let's say you have an input here and an output here. I don't need anything in between them. I can just literally just have any other non-related circuit here, which does not connect between this and this. So these are not even related. But I can still power from this input and then go somehow wirelessly to this output. So no actual circuitry needed in between these two positions. Very straightforward because this is a wireless transmission method. And circuits under this method require a very fixed setup, unfortunately, because you only have so many wireless transmission methods, unfortunately. And this kind of method also has a small fixed delay, regardless of distance. So the more distance you put it doesn't mean it will increase delay. In fact, it has a fixed delay even. So let's talk about, when they're useful. So why you would use a wireless transmission method? Well, first off is that you don't have enough space. You are desperate in terms of space. There's insufficient space to use one-way transmission methods or sliders. So you have a bunch of things that you want to wire here, and now you've realized, not really now you realize, but then you already know, kinda, that you won't have space to wire from this to here. It's just too much to use some of these space because you need them for other purposes. Then you use a wireless transmission method, or in some cases, it's literally impossible. Because, for example, you might have your door frame literally disconnected. Then what do? Wireless transmission methods. If you literally have your door frame disconnected, that's the only way out. And another situation where you would use them is that you have two distant circuits that somehow are very far apart, but then you need them to power almost simultaneously. Then you use a wireless transmission method. So yeah. Now I'm not going to go deep into what wireless transmission methods. Yeah. But hopefully, these kind of abstract description on the properties and the usefulness of these kind of different signal transmissions circuits help you understand, which type of circuit you should be using. So yeah. Okay. So that's the end of the signal transmission part. Now I'm going to talk about, some strategies of connecting different circuits. So the order of moves to power in the sequence determines which connecting method is the best. So I will summarize these kind of methods and introduce two new connecting concepts. They are also quite simple, actually. In fact, the entire video, if you haven't noticed, I'm talking about very simple things. But those are the things that, some people might forget. It is, sometimes I would like to call them common sense, but then it's not actually that common, unfortunately. So it's just a reminder on things that you have to always remember when you're trying to wire stuff more competitively, let's say. So anyway, so yeah, the connecting concepts. So let's summarize some connecting concepts that we have already covered throughout, basically, which, it should be very familiar for many of you. The first one is simply direct. Let's build some setup here. Let's call this A. Let's call this B. Maybe I have something like this. So this means that when one move is always followed by the other. So for example, when I power A, I always wanted to power B next. So I just use, for example, two observers like this. So it goes from A to B, A to B, always like that. So when would direct connecting be used? Well, first off is, the very obvious scenario where one always have to go follow the other. The second one would be a bit more not trivial, is that some moves might require some precise or irregular timings. It might not be necessarily that this move always follow the other, but then the irregular and precise timings require you to use a direct connection method. Because other methods, they might have some timings which you cannot have full control, but then the direct connecting method allows you to control your timings more precisely. So that's one of the scenarios where direct connecting is suitable. The second one is toggle. So when one loop has to power in some iterations but not the others. So for example, A, B, A. So I power A, then I power B, correct? If I have a piston as an output. But then the second time, doesn't power. Obviously, when I say toggle, here I don't mean a two-state toggle. I can mean a lot of variations of toggles, maybe a 3-state, 4-state, 5-state toggle, or even some other more variational toggles. Like, I have 5-state toggle, but then for the second and the fourth state, I want to power the thing. But the first, third, and fifth, I don't want to. So a lot of different variations. These are all classified into toggle. So just so you know. So this is a toggle connecting method. The next one is arbor. It's a bit more tricky to build this one, but then just use hopper. Very simple indeed. A, B, and then B, A. So you just imagine two pistons going up like this. So very simple. When your circuit has to do a sequence in the form of A, then B, and then B, then A. So hopper timer is usually the go-to method. And lastly, a two-distant pulse generator. For example, a burnout. When I power A, maybe I want to power B 2 times, but very far apart. So this is obviously useful when you need a large delay in between the two pulses. For example, maybe I want to do B and I do A, but then a long time after I want to do B again. So maybe now I want to power it, and then I power this here, and then power this. So yeah. So these are the 4 very common connecting concepts that I'm sure that you already know it, but then you didn't really need a name for it. But now I'm just telling you, just a review basically. Now the following concepts is also actually very simple, but sometimes you might not recognize it until it's too late. So that's why I'm here to remind you. So the concept is called conductor. Conductor is very simple. Again, I have multiple inputs, but I wanted to connect them to the same output. I think I have it here. Yes. Multiple inputs, but I want to connect it to the same output. Now, you can already see a relationship between this and the OR gate. The OR gate is also very similar. I have multiple inputs, but I want to connect it to the same output. Either one of them powers will cause the output to power, right? So it's very similar to OR gate. But then conductor is a bit more specific. It is a component that connects 2 different circuits. So for example, it can be a residual dust, it can be a hopper, it can be a node block, or it can be a dropper, anything like that. So why do I have to mention specifically about conductors? If somehow you have a circuit that you might not be aware that it needs to receive from multiple inputs. For example, you might recognize that there must be a connection from here to here, but you have not reserved a conductor to allow another input, say from here, to connect to here. Now, if you realize this too lately, then what will happen is that you have to rewire things, which is not nice. Obviously, here we can just add a hopper here, but then in a lot of the situations, it might not be that easy. So the message is that you have to make sure that when you are building some small circuits, you always have to make sure that you reserve the space and to plan conductors far ahead, such that you don't have to face the risks of rewiring stuff. Because this always happens. You might always have some situations where you have to power things multiple times, and then you thought one input is enough, but then apparently it's not. You need from other inputs. So make sure you reserve some conductors for that, and the space, of course, for establishing a conductor, because wiring an OR gate requires planning. So yeah, so that's the thing I want to remind you of. The concept itself is very simple, but then sometimes you might forget it, and you didn't plan it well enough that you have to rewire things, which is not nice. Okay, the second concept is actually a bit newer, and for observer doors, this actually occurs a bit less, but for observerless doors, this occurs a lot, which is post-link dependent circuits. And as the name suggests already, it's a circuit which does things differently depending on the post length. So the example here is very simple. This circuit only accepts pulses longer than or equal to 3 ticks or 6 game ticks. So a 2 tick here won't work, but a 3 tick here would work. Very simple indeed. So when do you see this kind of post length dependent circuits? The most common one is the double triple circuit, where a double, I think, corresponds to 3 ticks and a triple corresponds to 4 ticks. So yeah, this is very common. I think it is so common that people already know. So why do I, tell you this kind of circuit? Well, even though I say in traditional observerless doors this will be apparent, but that this will be more useful, but then sometimes in observable doors, it might be also useful. Now I just give you a very abstract example. Hopefully you understand what I mean. If not, then whatever. Doesn't really matter. But yeah, I guess before I forget it, one usefulness of post-dependent circuits is that they allow you to just use one input, and just by varying the pulse length, you get different jobs done. So if, for example, here, if I do a 1 tick, then it's very obvious what you would do. A 2 tick is actually very similar. Then a 3 tick is a bit different. And now 4 tick is different as well. This is actually not that of a good example. I should be using this instead. So 2 tick does this. 1 tick it will retract, but then 2 tick it won't retract. 3 tick it does something like this, and then 4 tick it is a bit more unique. It will do this. So yeah, so this is one kind of pulse-dependent circuit. Although I'm not sure how you would use it, but then just listening, because I think this appeared in my 780 block, though where I once wanted to use a what? Yes. Okay, I remember now. So the circuit I'm referencing is this. I will have an input here, which is connected to the other stuff, and then I have a 3 tick here. Oh, I think it should be. Just imagine it should be something like this. Where the top doesn't retract it, actually. So why is this useful? I have something like this. A double here, which I don't want to retract it. So this here will allow this to remain in this position. So this is useful. And it is technically a pulse-dependent one, because I have this here, and then I also have a pulse here. Technically. But yeah, either way. Still, the main idea about pulse length dependent circuits is that you only need one input, and by varying the pulse length, you get a different outcome. But yeah, either way. I think I will talk a bit more in the later videos, but then this is just an introduction. Yeah, I spent too long time on this. Anyway, let's move on. So after discussing these connecting concepts, and so these kind of two new, not so new, but I guess a bit more different concepts, then I will talk about something that is, I will talk about the wiring space restriction. So yeah, as I've already said, you heard about constricting your wiring in a small volume, but then within the volume, you might also want to restrict a certain component into a small volume, because you want to reserve space for other circuits. So yeah, so this kind of stuff is helpful in maintaining a balance between the volumes of each component. So let me just show you an example. So we have the 7x7 cave door. I have a previous build which actually uses one more layer at the top and also uses line blocks. Why the previous build has a larger volume and occupies an extra layer at the top is because of an inadequate wiring space. The sides uses too much space. It actually even occupies up to this level here. And the top doesn't have enough space to wire it, so I need to add another layer on top of it. Then obviously as time progresses, then I try to compact it, and which is the door you see here. Now, how do I do it? I improved the layout. So previously it has a layout something like this, but somehow this layout is more complicated than the standard double one. Even though the double one seems like it uses more space, but it's actually much easier to wire in this case. And I also put a wiring space restriction for the sides. Ignoring this slider push down thing, you can see that I actually restricted the size to be at the ceiling level. So this is actually the ceiling level, which I actually done it, you know. So the idea is just to set a smaller goal on your components. You set a larger goal on your volume, but you set some small goals on your different components. Yeah, and this ensures that the wiring space on top is enough for all the complicated stuff it needs to do. Now this is a very short example, but then it is very much related to the next example. Oh, sorry, the next topic that I want to say, which is the circuit section working order. So when a door has multiple components, it's correct. When the door has multiple components to wire, there are several possible working orders. So I would like to summarize the main working orders and to give you some advantages in terms of the psychological effects and also in terms of wiring space restriction as well. So this also enhances the reason why I need to talk about the wiring space restriction, is because it does affect in how you would construct a door. So let's see. I have a few working orders, including the first one is motivational. So the working order is based on motivation. So you can have, for example, you work on a door from the most motivated part to the least one. So you work on the one that you want to work on the most to the one you want to work on the least. Or the reverse. You work on the one that you want to work on the least to the one you want to work on the most. The former one, obviously, it will help you to start your building process, but then, you might suffer a bit later and want to give up, basically. But then the latter might make you, I don't want to work from the start. But if you have survived this kind of period, then it will be much better for your later work. Now, the advantage of this is basically, depending on your style, is basically to help you to work on the door in terms of motivation. Some people prefer to, work on the things they want to work on the most. Some people prefer to work on the things they want to work on the least. It just basically helps you to get your door done. This kind of method. So this is the advantage of it. But then, this comes with a disadvantage. Is on the wiring space restriction. Let's say for this door, I somehow want to work on the bottom first and then the top and then the sides. Then what will happen? you need to plan ahead how much space you want to reserve for the size, because size is the latest part you want to work on. And that might be difficult. So you have to bear in mind that if you're working in some orders like this, then you need to plan very far ahead on what you are trying to achieve. Otherwise, if you plan it wrong, predict it wrong, then it is not good. You have to rewire some things. Not nice. So yeah. Also, you're jumping over different components. You also need to switch your mindsets constantly. This might be good for someone, but bad for someone as well. So, like if you have a very flexible mind, obviously you can do that. But if you don't, then there will be a certain working order that will be suitable for you. The second one is difficulty based. So the order is based on the difficulty of the circuit section. It might be easy to difficult or difficult to easy. Now, difficulty is sometimes correlated to, motivation. It's like some people think that the easier ones are the ones that they want to work on the most, which is very straightforward. Then these two methods share similar properties, basically. So the difficulty based shares some similar properties with motivational based. Now, but then difficulty based is actually require a bit less in terms of planning in wiring space restriction and switching between mindsets. The thing is, I haven't talked about motivation. It can be very extreme. Extreme as I want to work on the bottom triple, and then maybe the slime extender, then the top triple, and then going back to the bottom double, and then so on and so forth. So it can be very constantly switching, and you can already see this isn't a very nice kind of way of doing stuff. You need a lot of planning to see how other things will fit in. So yeah, you just jump over and over. But then difficulty based usually is a bit more clustered. You would cluster the bottom as one section, top as one section, sides as one section. So, yeah. So that's why I say you don't need to plan that as much as the motivational one. Although you still need to plan a bit more than the one that I'm going to talk about a bit later. So a bit less, but still more in average. Yeah, and it's also, of course, the switching between mindsets. Difficulty based requires a bit less than the motivational one, but then still more in terms of the average. Now, another thing about difficulty based is that, for example, you work from the easy to difficult, okay? If you didn't plan your wiring space restriction good enough, it might turn out that your easy part occupies too much space for the difficult parts, and you need redo. But it's difficult to easy, it will help you determine the space that the difficult part has. And the easy part, you can, wiggle around stuff. And because it's easy, so, more often than, you can adapt to it better. But of course, because you build the difficult part first and then you build the easy part first, and the easy part might turn out to have a bit less space than you expect, and you have to have more creative mind, which also pushes up the difficulty of the easy part. Like the difficulties of the parts depend on each other. So that's one thing you have to bear in mind. Now, the last part, I think this is the thing that most people do already. The difficulty and motivational parts, they sound very radical and extreme. The last one is the geographical. We will work on, we will have a working order based on the position of the circuit section. Maybe from top to bottom or bottom to top. That's the most straightforward. And the reason why this is regarded one of the best methods is because you don't have to plan that much in wiring space restriction. Because for other working orders, what you need to do is to jump over. But then if you don't have careful planning in terms of the space that you're going to use, then chances are you're very likely to mess up. But for the geographical one, because I work from a certain order to another, from a circuit components to the one that is next to it, then I'm going to mess up a lot less. Yes. Yeah. And because I have, for example, bottom to top, this is fixed already, then I already exactly know what space I've occupied. Then I can just work on here based on the fixed space here, and then work on it. And then this is now fixed, and then the top. So, the need of planning for wiring space restriction is a lot less. You also don't need to jump between mindsets. Now, in terms of motivation difficulty, if that's what you're considering, it's actually mixed on average. Because you expect in the long term, the parts that you're going to work on in terms of the geographical is just basically very sensitive. You can say. You might first have a door that will work on medium, easy, difficult, and then the other one difficult, easy, medium, something like that. But then on average, it will just go into a certain direction where it's just basically the same, medium. So they'll behave very similar. So it is on average mixed, you can say. So yeah. So you can formulate again your opinions on which one works the best for you. Because Redstone is kind of an art as well. Besides, the technical aspects that you have to learn. Redstone is still some form of art, which different people will do different things that will suit their own needs, and different people formulate different opinions, and that's completely fine. But just importantly, you have to plan on stuff, otherwise you're just going to redo a lot of times and it's a lot less fun. So the moral of the entire video is that plan on your stuff, think carefully what you want to do. For example, the circuit flow, what you want to do, the input position, where you want it to be. Think it along with the sequence, of course. And then how to wire it, so the connecting concepts. And also where to start and where to end. So just think of these ahead, and I'm sure along with some good actual wiring skills, then you'll master stuff. So yeah, and in the documents, I already included all the useful resources in which the planning steps are also going to be discussed. The first one is 1-5 input methods. I actually talk about these two doors in 1-5. And at that time, I advertised it as a taste of planning, and this is the video we are watching now. And yeah, I promised that I'll talk about these two doors a lot deeper, which I did now. The second resource is the introduction to planning and sequencing, because these are not the only planning steps you need to do. You also need to prepare some stuff before you actually even build the door. So, go watch that if you haven't. And of course, I have some explanation videos throughout. So, in case if you're interested in watching how the door is made and, some in-depth knowledge on each of the door, then you can go watch that out. All of those will have some links. And yeah. Now go on to the exercises. Now the exercises here, because we are already talking about in a much higher advanced level, what I want you to do in these kind of exercises is you have to imagine yourself actually building the door. You cannot just answer the questions with less thoughts. You have to really involve into it. You need to think of how you're going to build the door. Of course, the questions themselves are also directed in this. That it engages you to think, okay, if I'm actually building the door, what I should think of. So the questions already, give you a direction on what they will actually happen. And these two doors are actual doors that I've built. So I can, point you in certain directions in terms of the questions. So go ahead and try to do them. They're mostly word questions, because planning is, a lot of thinking and a lot of reasoning instead of a lot of building in terms of the circuits. So unfortunately, I'm not going to tell you to build circuits, except for one sub question where I ask you to modify the layout a bit. But yeah. Now, the thing I want to say about the question is on this one, because this one has a more complicated example. It's a 4x4 customizable door that I've built, and I've given you a partial layout. It's not partial anymore. It's the full layouts with the powering layout. And the remaining things that is missed out is just the circuitry on controlling them. The thing I want to talk about is this. We have A, B, C. A is the storage and singles. B is the doubles. C is the triple. So in sub-question D, I have a general sequence. The closing is CAB and opening is BAC. And I have this kind of bracketed information. I say moves will be removed depending on the pattern. So you have to remember that because this is a customizable door, what it means is that besides the standard all 4 blocks will be filled, I can have this block removed, 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 depending on it. And moves will be removed depending on which block I removed, basically. So, let me see. As a small example, let's say I remove this block here. Then you would remove, I think it's B. So you would do C for the closing to get the triple out, and then you would do A to have this block here for seamlessness. So you read something like this. So you have to make sure that for every combination of the pattern, you can find a sequence by having the entire general sequence or just removing some moves, and they will still work. You have to make sure that all of the combinations will work. So yeah. So that's why I say you have to really engage in the actual door. You have to think it as if you're building the door to understand, some planning steps. Because otherwise, you're not planning at all. You really have to think about when you're actually building the door. Okay, then does this work? Does that work? What should I do? Etc. Etc. So yeah, hopefully the questions are enlightening to you and also fun, I guess. And I guess most of all, I hope that I helped you in terms of thinking better. Perhaps all of these concepts might be very simple, but then they're also important. Obviously, you don't have to recite them every time you're trying to build a door, but then just keep them deep in your mind, what you should do, basically. So yeah, once again, the documents, world download, they're all in the Drive folder, and they are going to be linked in the description below. And the next episode is going to be 3-3 sequencing, because we cannot plan without a certain sequence, obviously. And sequencing, as I already say, is also part of the planning. And yeah, in the next episode, it will be sequencing. Then I will talk about how we actually establish sequences. And then we can do some more planning on top of these established sequences, and how to construct sequences, how to, modify, improve the sequence. Yeah, all those kind of knowledge will be covered there. So yeah, thank you for watching this video. If you liked it, and I'll see you in the next one.